One of the most important concepts in thermodynamics is the idea of specific heat. If you're looking for information about it, you've found the right video. We'll clarify some facts about specific heat and do a simple problem. Let's take a look at the heat transfer equation, delta Q equals mc delta T. Remember that in this equation, delta Q is the heat transferred to or from the object. M is the mass of the object, C is the specific heat, and delta T is the change in temperature. Let's solve this for the specific heat times the mass. This gives us Cm equals delta Q over delta T. This shows us that the mass times the specific heat capacity of an object is the amount of heat that is transferred to the object for a given change in temperature. This is sometimes called the heat capacity of the object and may be denoted by a capital C. Notice that the heat capacity depends on both the material and the mass. A larger amount of the same material could hold more heat than a smaller amount. To remove the mass dependence, we divide by the mass, ending up with C equals delta Q over the quantity m delta T. This is the specific heat capacity of the object. Notice that it is the heat capacity per mass unit. By defining this quality, we can look up information by type of substance rather than by the size or mass of the object. Let's assume that we add the same amount of heat to two objects with the same mass but different specific heats. Notice that in the heat transfer equation, the specific heat and the temperature change are on the same side of the equation and multiplied by each other. This means that for materials with a higher specific heat, the temperature change will be smaller. Likewise, for materials with a lower specific heat, the change in temperature will be larger. If you are finding this video to be helpful, please tap the thumbs up button to like. If you really like my style of teaching, please subscribe. If you have any questions, please ask them in the comments below. Be careful about wording here. The heat capacity is the amount of heat that an object can hold. The specific heat capacity is the amount of heat per unit mass. Sometimes we refer to the specific heat capacity as simply the specific heat. The specific heat capacity, or simply specific heat of a substance, can be found in standard reference tables in textbooks, handbooks, or on the internet. These tables are from the OpenStax University Physics book. Different materials have different specific heats. This is due to the molecular mass, the structure, and the binding energy of the materials. The specific heat can also vary by pressure or temperature, particularly when working with gases. It also varies by phase. For example, ice, water, and steam all have different specific heat capacities. When doing problems in an introductory physics class, I'd suggest that you look up specific heat values in the textbook rather than online. If you look things up elsewhere, you'll often find that many values are available. Sometimes this has to do with the purity and/or particular alloy mixture. Other times you'll find specific heats with other units. Note that the specific heat values here are given in units of joules per kilogram Celsius degree. Since the temperature in this equation is a change in temperature, we can use K or C interchangeably. Therefore, you may also see units listed as joules per kilogram Kelvin. Note that we can change the heat unit, the mass unit, or the temperature unit. In chemistry class, you may also see units of joules per gram Celsius degree, calories grams per Celsius degree, or joules per mole Kelvin, or other variations. When you look up the specific heat of a substance, be sure to use units consistent with what you have measured or have been given. If you know the mass of an object, its temperature change, and how much heat it has absorbed or released, you can determine its specific heat. Let's do a simplified example. A metal object with a mass of 0.500 kilograms is placed in boiling water and has its temperature raised to 100 degrees Celsius. It is then placed in a separate container of water where it loses 5,010 joules of heat and ends up at a temperature of 77.5 degrees Celsius. What is the specific heat of the metal? What material is it likely to be? We start out with delta Q equals negative 5,010 joules. The negative lets us know that the heat has been taken away from the metal. The mass is 1/2 of a kilogram. The starting temperature is 100.0 degrees Celsius because it was in boiling water. The final temperature was given as 77.5 degrees Celsius. This leaves us only the specific heat as our unknown. We start out with our heat transfer equation, delta Q equals mc delta T. We solve this for C, which is equal to the fraction delta Q over the denominator, m delta T. Putting in our values, we have the fraction with numerator, negative 5,010 joules, and denominator 0.500 kilograms times the quantity, 77.5 degrees Celsius minus 100.0 degrees Celsius. Putting this into our calculator gives us a value of 445.33, which has a few extra digits. The units are given by the fraction negative joules divided by kilograms negative Celsius degrees. Notice that the signs of the heat loss, negative, and the temperature change, also negative, cancel out. This leaves us with a positive value of 445 joules per kilogram Celsius degree to the proper number of significant digits. To determine which material this is, we need to reference a table of specific heats. Note that this specific heat isn't exactly a value found on the table I showed earlier. However, it is reasonably close to 452 joules per kilogram Celsius degree. Thermodynamics experiments are very sensitive to conditions. To get very good results, you need to have a weighted measured temperature accurately. In this example, if the temperature had been measured to be 77.83 degrees Celsius instead of 77.5, the answer would have been exactly 452 joules per kilogram Celsius degree. The value of negative 5,010 joules is questionable. You might be wondering how we got that value. We typically have thermometers, not heatometers. Temperature is very easy to measure, but heat is difficult to measure. We often measure the temperature difference of two or more objects with known specific heats in a process called calorimetry. We'll look at that in the next video. In practice, this usually involves more than one substance and some type of insulated vessel.